In this video, I will explain how to write a vector in components. There are two different ways to write vectors in 2D, and you always need two pieces of information. And you can either do components or magnitude and direction. So this video will talk about how to write a vector in components. The sort of picture you want to have in mind here is you want to think of a rectangular coordinate system. Actually, let's leave a little bit more space. You want to think of a rectangular coordinate system. And also sometimes that is called Cartesian. You might have heard that before. So a Cartesian or a rectangular coordinate system. Usually we do x on the horizontal and y on the vertical. And if I just sketch a quick vector here, put it at the origin, no special angle, label that vector v. I like v, of course, in physics v is evocative of velocity. In terms of how I would write this as a vector, I like to do an arrow over the top in handwriting. Lots of books will use boldface, and I really like to use column vectors. So I put the vx, the x component, on the top, and the vy, or the y component of the vector, on the bottom. There is lots of different notation for this. A lot of books will do something like the vector v is equal to vx in the I hat plus vy in the j hat. You'll also see, I'll explain that in just a second, you'll also see vx x hat and vy y hat. For the first time I saw something I don't know if I really like. I saw somebody write vx vector plus vy vector. It's not wrong, I just usually think of the components as not really being vectors, that they have a separate notation for that. But that's fine, I said nothing wrong with that. So there's some new notation there, the hats over the top of the vector. So I am using the arrow over the top to indicate a vector, the hat over the top, so just the hat part, indicates that it is a unit vector. And so the hat indicates a unit vector. Unit is another way to say 1. So a unit vector simply means that the vector, whatever it is, has a magnitude of 1. So the length of the vector, the magnitude of the vector, is 1. That means when you multiply by an I hat or an x hat or a y hat or a j hat, you don't actually change the number. So by multiplying by 1, you don't change the value of the vector itself, and so it just indicates direction. So the I hat and the x hat indicate the x direction, and the j hat and the y hat indicate the y direction. So those are two notations you'll see in different textbooks. I'm actually not going to use it. Like I said, I'm going to use the column vector very often, especially when we start using vectors in the middle of equations. So what does it look like on the picture? On the picture, and I'll write this, what it looks like, the x component is the projection of the vector onto the x-axis. So this right here is what I would label v sub x. And it goes, I guess it does go in the plus x direction. Then the y component is the projection of the vector onto the y-axis. So this direction right here, this piece right here, is what I'd label vy. You also, lots of times people will draw the vy over here. That's perfectly fine. I guess when I'm putting arrows on them, they are vectors. So that's the x component and the y component of the vector. How do you get them? So if you are given the v as, given the v as magnitude and direction, you can use the trig definitions of the sine and the cosine to figure out which is which. So the cosine of an angle, so let's label that theta on that picture. It's standard to use this as theta, but you always want to make sure in the middle of a problem that that's actually the one they're using if there's a given angle. The cosine is defined as the adjacent side of the triangle, so adjacent to that over the hypotenuse. If you look at that picture, the adjacent side, the one right next to the theta, is this side. So the theta's here, obviously this side of the triangle, so this side is the side right next to that theta, so that's the adjacent side. So the adjacent side over the hypotenuse means that it's the Vx side over the V. Now we're not using any vector arrows there on purpose, so that those numbers without a hat or an arrow over the top means the magnitude only. I can rewrite this, just cross multiply, and get that V sub x equals V times cosine theta. That is how to get the x component. And similarly, I can use the sine. The sine of theta is the opposite side over the hypotenuse. If I go back to my picture, theta's over here. There's the theta, and the opposite angle from the opposite side from that is this one. So this side is the opposite side. That's my V sub y. And again, the hypotenuse is always the long side of the triangle, and it's just the same, the magnitude of the vector v. I can cross multiply again, multiply both sides of this and this by the v, and I get that vy equals v times sine of theta. Let's do a quick example and see how that works in practice. Suppose that you throw a ball, you throw a ball with an initial velocity of 15 meters per second at an angle of 30 degrees with respect to the horizontal. This is something that might come up in a typical projectile motion problem. Then I'll ask, what are the components of that velocity vector? What are the components of velocity in this case? Oh, it's always a good idea to draw a picture. Once you get really good at these, you won't have to worry about it too much for something this simple. But as long as we're here, let's go ahead and do that. Let's draw a quick picture. Sketch my velocity vector. V looks similar to my last one. So that is the 15 meters per second. And then it tells you at an angle of 30 degrees with respect to the horizontal. So I've drawn my x along the horizontal, and that makes my 30 degrees the same exact thing as the theta that I was using in the last slide. So we can just use those formulas directly. The x component, v sub x, equals the magnitude of the whole vector times the cosine of the angle with respect to the x-axis. This would be just the 15 meters per second, and then the cosine of 30 degrees. If you plug that into your calculator, you will get 12.99 meters per second. Usually in my class we keep 3 sig figs, so that would be 13.0 meters per second. It's the x component of the vector, so I don't need a direction, but notice that it does have units. And let's also do the y component. Same thing, direct application of the formula. V sub y is equal to v sine theta. If you go up and look at the picture, that's the component over here, v sub y. Same thing as the projection onto the y-axis. That side of the triangle parallel to the y-axis. It's the opposite side from this 30, so it's the sine. Opposite goes with sine, and again I plug in the magnitude of the 15 meters per second, and this time it's the sine of 30 degrees. So the sine of 30 degrees, and I plug that in, and that's exactly half. Sine is a half, so I get 7.5 meters per second for the y component. So again, for my notation, if I were going to write this final vector, I would write vector v equals, I would write the 13.0 for the x and the 7.5 for the y, and I'd probably write the meters per second out here at the end to go with both. So there's a quick example of writing a velocity vector in terms of the x and y components.